Good day, my name's Jane Morris, and in this presentation I'm going to cover the risk assessment of genetically modified insect-resistant maize, known as Bt maize, for food and feed use, with special emphasis on its safety for people in southern African countries. In this presentation I'll briefly cover, firstly, what is Bt and what is Bt maize? How does it work to control insect pests? Where is Bt maize grown around the world? And how do we assess the risks for food and feed? And then I'll take you through a full risk assessment for one particular type of Bt maize as an example. So, firstly, what do we mean by Bt? Bt stands for Bacillus thuringiensis, a type of soil bacteria that produces a variety of protein toxins that are active against insect larvae. The majority of these proteins are produced as crystals in the bacterial spores, so they're called cry proteins for short. Many of these are quite specific. So for instance, cry-1 toxins are active against lepidopterans, that's moths and butterflies. Cry-2 are active against lepidopterans and dipterans, that's flies and mosquitoes. Cry-3 are toxic to coleopterans, beetles and weevils, and Cry-4 are toxic again to dipterans. There are many more different types of cry protein toxins, but these are probably the groups that you're most likely to encounter. There are also some toxins that are produced in the vegetative stage of growth of the bacteria, and these are known as VIP proteins. They're active against Coleoptera and Lepidoptera. The toxins bind to receptors in the insect midgut, forming pores and causing osmotic shock so that the insect larvae stop feeding and die within a few days. Bt toxins are generally regarded as safe to humans and animals because mammals don't have receptors in their guts for the proteins. In fact, Bt toxin sprays are regarded as very safe, and to the extent that they're widely used in organic agriculture as a so-called natural alternative to chemical sprays. In a short presentation like this, I can't cover all the different types of crystal proteins, so I refer you to the article shown here in the Journal of Invertebrate Pathology if you would like to read up some more and get some more information. A variety of Bt genes have been engineered into maize to give resistance to different insect pests, and Bt maize is grown in many countries, including the USA, Argentina, Brazil, Spain, and of course South Africa. In many cases, the insect resistance is combined with herbicide tolerance, and there is now an increasing tendency to stack several Bt genes together within a single plant. Since South Africa is already quite well advanced in its use of GMOs, it's useful to know what Bt maize events are already approved in South Africa. South Africa has a system called commodity clearance, whereby GMOs can be approved for use as food or feed, but not yet for cultivation. A number of these events approved for commodity clearance are for imported maize, which may be further exported to other countries in the region, often being milled first, depending on the requirements of the country concerned. Many of these approved maize events are also available in stacks with other genes. So approved events include maize transformed with genes from the Cry-1, Cry-2 and Cry-3 families, as well as one vegetative VIP gene. And of these, 4 of the events are fully approved for commercial cultivation in South Africa. Mon 810 was the first to be approved way back in 1997. In order to work through a risk assessment of Bt maize for food and feed, we need to remember the normal procedure that we follow for risk assessment. So the steps are, firstly, hazard identification, i.e. what might go wrong. And note that this is not the same as what might change, since all change is not necessarily for the bad. We then ask, how serious would the consequences be if something did go wrong? That is, what would be the harm? And how likely is it that the harm would occur? The overall risk is then assessed as being a combination of harm and likelihood. And finally, a decision is made on the basis of the acceptability of the risk that's been assessed. And at this stage, there may also be taken into account the expected benefits. So, for BT maize, we can ask the following questions to help us identify any hazards that relate to food and feed safety. Firstly, is the DNA stably inserted with a single site of integration? And that's an important question to ask in terms of identifying any possible unexpected effects. Next, is the protein toxic to humans or animals? Is the BT protein allergenic? And are there any changes in composition of the maize? Particularly, are there any changes in anti-nutrients, such as phytates and protease inhibitors? And could there be any longer-term effects from eating the BT maize? And finally, because this is an environmental issue rather than a food safety issue, would it be a problem if unmilled maize grain fell from trucks or was planted by farmers? We then follow these questions through the risk assessment process, and I'm going to use one example, the BT maize event Maize 604. In a short presentation like this, I can't go into the full details, obviously, of all the data, but I will attempt to summarise the important facts. We start by looking at the inserted genes and their stability and expression. Maize 604 contains the Cry3A gene, and it was developed by Syngenta to have resistance to the corn rootworm. There has never been any application for it to be grown in southern Africa because corn rootworm is not a pest in the region. It was approved for importation for food and feed use in South Africa in the year 2011. In addition to the Cry3A gene, Maize 604 contains a gene for the selectable marker phosphomannosisomerase, the PMI gene. Single copies of both genes are stably inserted. The Cry3A gene has been codon modified to increase expression in maize, but no other changes have been made. The PMI gene comes from the bacterium E. coli, and it enables selection of the transformants on a growth medium with mannose. It's been established that there was no DNA inserted from the backbone of the transformation plasmid, so only the intended genes were inserted. And expression levels of the two proteins in grain were measured at 0.7 micrograms per gram fresh weight for Cry3A and 1.9 to 2.6 micrograms per gram fresh weight for PMI. Next we look at toxicity and allergenicity. Acute toxicity studies are normally carried out with the isolated protein because it's not possible to get a sufficiently high level of intake with the whole feed. So an acute oral toxicity study with isolated Cry3A in mice showed no effect at the highest level of 2,377 milligrams per kilogram of body weight, and for phosphomannosisomerase, no effect at 3,080 milligrams per kilogram of body weight. Bioinformatics sequence analysis showed no homology with known toxins other than the crytoxins themselves. In terms of allergenicity, Cry3A and phosphomannosisomerase are both rapidly degraded in gastric fluid, whereas allergens are normally stable. Again, bioinformatics sequence analysis showed no homology with known allergens at the 8 amino acid sequence level, apart from phosphomannosisomerase showing some homology at this level to an obscure allergen from a species of frog. But further study showed that this area of homology did not correspond to the allergenic epitope. We then go on to see if there are any compositional changes. This is done by comparison with a near isogenic conventional maize line, bearing in mind the normal compositional range of maize. Useful information on maize composition is available in the OECD consensus document, and I give the link to the document here. Maize does contain some anti-nutrients, particularly phytates, raffinose, and trypsin and chymotrypsin inhibitors, so it's important to check for any changes in the levels of these compounds. To test for compositional changes, Maize 604 and its near isogenic conventional counterpart were grown in 13 locations over a 2-year period, and the grain composition was compared. Proximates, minerals, amino acids, fatty acids, vitamins, anti-nutrients and secondary metabolites were measured. Proximates included crude protein, crude fat, moisture, ash, carbohydrate, acid detergent fibre, neutral detergent fibre and total dietary fibre, while minerals included calcium, phosphorus, magnesium, copper, iron, manganese, potassium, sodium, selenium, chromium and zinc. And the vitamins included beta-carotene, cryptoxanthin, folic acid, a range of B vitamins, vitamin C and tocopherols. The anti-nutrients included the phytic acid, trypsin inhibitor, raffinose, and then a range of secondary metabolites were also tested. So there were some variations noted from the near isogenic control, but all the values were within published literature ranges for maize. So in conclusion, no hazards were identified that would make the maize unsafe to eat. The risk assessment at this point indicates a negligible risk. However, the question's often asked, but what about the long term? How can we know that this GM food won't give rise to health issues years ahead? Well, firstly, we need to bear in mind that people have now been eating GM maize for almost 20 years, with no ill effects recorded. The problem is that doing longer-term feeding studies has a number of weaknesses that are not necessarily going to detect adverse effects. And I refer you to the paper shown here for a detailed discussion on this matter. With this in mind, the European Food Safety Authority recommends longer-term feeding studies only when specific hazards are identified to justify them, and this was not the case for Maize 604. But despite the European Food Safety Authority recommendation, EU regulations now require 90-day rat feeding studies for all applications, and so this has been done for Maize 604, as well as a 49-day poultry feeding study. No adverse effects were seen in either study. Of course, we do need to take into account that in southern Africa, maize is a staple food, unlike in Europe or the States. Of all the countries in the region, Lesotho has the highest consumption at 174 kilograms per person per year. However, the acute toxicity tests showed no adverse effects at consumption levels more than 1,000 times greater than the daily consumption in Lesotho. The 90-day feeding trials also showed no adverse effects at the maximum dosage that it was practical to feed. We can also take into consideration the fact that the Cry3A and PMI proteins are rapidly destroyed by heat when maize is cooked, so the food that is eaten would not contain the active protein. It's also very unlikely that the total intake of maize would consist of Maize 604, although even if it did, it is very unlikely that there would be negative effects. So this means, in total, that the likelihood of adverse effects, even in the long term, can be considered to be negligible. We can then reach the overall conclusion that the risk for food and feed use is negligible and Maize 604 is safe for people in southern Africa to eat. So now, finally, we consider any environmental risks if some grain is spilled or if farmers retain and plant some of the grain. Of course, this is only an issue in the case of whole grain, not milled grain. The Cry3A protein in Maize 604 has activity against the coleopteran pest corn rootworm and other related coleoptera in the family Chrysomelidae, but these are not pests in southern Africa. The coleopteran soil pests in southern Africa are the black maize beetle, which is a scarab beetle, and the false wireworm in the family Tenebrionidae. Cry3A has been shown to have some limited activity against another beetle in the Tenebrionidae family, but only at high levels. It's therefore unlikely that Cry3A would give maize any selective advantage in the southern African context. So if any maize plants were to grow, they're unlikely to have competitive advantage over conventional maize plants that would make them more weedy or invasive than conventional maize. In any case, any volunteer plants could easily be killed with herbicides. If farmers planted the maize, we've already established that it would be as safe to eat as conventional maize, and it is in any case an annual crop that can be easily controlled, and it would lose hybrid vigour over successive seasons. So, as a final conclusion, we can say that the risk of importing Mir 604 grain into the SADC region for food and feed is negligible. There is also no reason why there should be a specification to mill the grain, as the whole grain poses negligible risks. This then is just one example of a risk assessment, and of course each BT event needs to be assessed on a case-by-case basis. But hopefully by giving you this example, I've given you the confidence to be able to do your own safety assessments on other events in future. Thank you.